Today we're going to talk about the scientific revolution. So while some people were getting into boats and going all over the world, while the Spanish were throwing out the Arabs and the Jews and remaking Spain in their what they believed was a Christian Spain, while many other developments were occurring in the Reformation in Europe, there was also a scientific revolution beginning to take shape. And today we're going to talk about some of the important topics, especially the ones that affected Christianity and the way people thought about the world in that time period. And the dates up here, 1543 to 1687, we're starting basically with the ideas of Nicholas Copernicus in 1543. And I don't have a slide for this, but I would just preface all of what I'm about to say with Proverbs 25, verse 2. It is the glory of God to conceal a matter, but the glory of kings is to search out a matter. So we are made in the image of God. We are made like him in so many ways that we think God's thoughts after him, and God in his sovereign providence allows human beings to discover aspects of the creation that human beings did not know at a certain point, and then they begin to know them, and that begins to shape all of society. Okay, so the scientific revolution was a series of events that marked the emergence of modern science during the early modern period. Developments in mathematics, physics, astronomy, biology, including human anatomy, and chemistry transformed the thinking of people in Europe about man, nature, and God. Many of the developments in the sciences during this time challenged the prevailing Christian worldview. The emerging ideas of the scientific revolution served as part of the basis for the Enlightenment. And we will be talking about the Enlightenment. If you don't know what that is, I will enlighten you. I couldn't resist, sorry, had to make that pun. And we are on the way to the Enlightenment, but we're not there yet, and we need to lay the foundation for it. The 1543 publication of Nicholas Copernicus's On the Revolutions of the Heavenly Spheres is often cited as marking the beginning of the scientific revolution. Copernicus offered an alternative model of the solar system to Ptolemy's geocentric system, which had been widely accepted since ancient times. And up here on the screen, you can see a portrayal of what a geocentric system would look like. So in other words, in the geocentric way of thinking, the Earth is at the center of this particular part of the galaxy. And these planets that we are familiar with, that human beings from ancient times had been able to look up into the night sky and see. They had been able to see Venus and Earth, and Saturn, Mercury, and so on. And of course, everybody knows what the sun is. From a geocentric system, and you could see how people, especially ancient people who are using just their unaided eyes to look at the heavens, it appears that these things are moving around the Earth, and they were not aware that in fact the Earth is moving, and it moves not only in an orbit around the sun, but it also moves on its axis. It's moving in different ways. But from the perspective of earthbound humans, it appeared that the sun, moon, stars, and so forth were the celestial bodies that were moving around the Earth. Now, a big question here is, what is the significance of a geocentric system versus a heliocentric system? So when we say helio, we're referring to the sun. It's derived from a Greek word. Now, the Ptolemaic system developed by the Hellenistic astronomer Claudius Ptolemaeus in the 2nd century AD had standardized geocentrism. Again, this idea that the planets and the sun are revolving around the Earth and the Earth is stationary. His main astronomical work, called the Almagest, was the culmination of centuries of work by Hellenistic, Persian, and Babylonian astronomers. For over a millennium, European Christian and Middle Eastern and African Islamic astronomers assumed it was the correct cosmological model. And some Christians pointed to specific Bible passages that seemed to support geocentrism. For example, some asserted that Joshua 10, verses 12 through 14, shows that the daily apparent motions of the sun and the moon are due to their actual motions around the earth, rather than due to the rotation of the earth about its axis, or, I would also add, in its orbit around the sun. So Joshua 10, 12 through 14 is that famous passage where the sun and moon stop. Then Joshua spoke to the Lord on the day when the Lord turned the Amorites over to the sons of Israel, and he said in the sight of Israel, "Sun, stand still at Gibeon, and moon at the valley of Ajalon." So the sun stood still and the moon stopped until the nation avenged themselves of their enemies. Is it not written in the book of Jashar? And the sun stopped in the middle of the sky and did not hurry to go down for about a whole day. There was no day like that before it or after it when the Lord listened to the voice of a man, for the Lord fought for Israel. Okay, so again, if you're standing on the earth and you're observing the sun rise in the east and set in the west, as we do every day, the assumption is, excuse me, that the earth is stationary. It's the sun that's moving. But if you look at it from a different perspective, you could see the sun moving. You know, for example, if you're not standing on the earth, if you're standing outside the earth, which of course we can't actually do, if you're standing outside of the earth, you would observe different types of motion. If you were standing, for example, on the sun, you would observe the earth moving, okay? So it's a matter of perspective. It's a matter of reference points. Now, on the basis of this verse, and there's a few others, Christians are saying, well, this proves that the sun and the moon move, but the earth is stationary. For ancient and medieval Christians, the idea of the earth as occupying the center position of the universe is supported by the creation account in Genesis. If the earth is where God placed man, and if the earth is to one day be filled with the glory of God, then the earth is central to God's purposes. The other celestial bodies have their place in the firmament, and they serve as signs and for seasons and days and years, and they shall serve as lights in the expanse of the heavens to give light on the earth. Genesis 1, 14 through 15. So it's the idea that the earth is at the center. It's in the center of God's purposes. It is, we know today, the only planet so far that we know that has any type of life on it. Now, just because the earth is central to God's purposes, it does not necessarily follow that the earth is at the center of everything. It's not necessarily having to be the center of the universe in order to be the center of God's purposes, such as we understand them. Another scripture cited as support for a geocentric system is Psalm 93:1. The Lord reigns, he is clothed with majesty. The Lord has clothed and encircled himself with strength. Indeed, the world is firmly established. It will not be moved. And so many Christians interpreted that portion of Scripture, it will not be moved in a very literal way. The earth does not move. For many, as far as what could be physically observed and what was assumed based on ancient writings and religious texts, the sun, planets, and stars appeared to literally revolve around the earth. Now, some ancient Greek and medieval Islamic scholars did question the idea that the earth was stationary and that the earth was the center of the universe. Now, Nicholas Copernicus appears on the scene, and towards the end of his life, he proposed a heliocentric system. How did he come to the conclusion that the system where we locate Earth is centered around the sun, with the planets revolving around the sun? His conclusions were not based on physical observations, largely. His assertions were based on the work of Islamic astronomers that supported a heliocentric system and described the movement of the Earth in such a system. And there was the beginning of, during this time, there was a beginning of using the idea of we can use mathematical equations to describe these things. So, the idea of using math and geometry, trigonometry, and so forth to begin to understand physical phenomena is just beginning in this part of history. So as not to get in trouble with the church, his work on the revolutions of the heavenly spheres had a preface written by a Lutheran theologian, Andreas Osiander. Osiander stated that Copernicus had simply developed a mathematical hypothesis, just an idea, not an account that contained truth or even probability. The work also contained a letter from the Archbishop of Capua urging Copernicus to publish his theory. In a lengthy introduction, Copernicus dedicated the book to Pope Paul III. He noted the inability of earlier astronomers to agree on an adequate theory of the planets. And he also suggested his system would allow the church to develop a more accurate calendar. The Copernican system was widely criticized in Europe. Tycho Brahe, a Danish nobleman and astronomer, appreciated the elegance of the Copernican system. Mathematically and logically, it solves some issues that the geocentric system couldn't explain very well. But he objected to the idea of a moving Earth on the basis of physics, astronomy, and religion. The Copernican revolution took more than a century to displace the widespread acceptance of the geocentric system with the heliocentric system. While not warmly received by his contemporaries, his model did have a large influence on later scientists such as Galileo and Johannes Kepler, who adopted, championed, and sought to improve it. Some astronomers did acknowledge that Copernicus' system more adequately explained the four seasons by showing that the Earth's axis is not perpendicular to its orbit. In fact, that the Earth wobbles on its axis, so to speak. During the 17th century, several further discoveries eventually led to the wider acceptance of heliocentrism. Johannes Kepler's 1609 work, Astronomia Nova, showed that the orbits of the planets were elliptical rather than circular, while retaining the heliocentric concept. And Kepler's work solved more problems, more astronomical problems in terms of predictions of how planets would move and their positions because of his elliptical orbit idea. Using the newly invented telescope in 1610, Galileo discovered the 4 large moons of Jupiter, evidence that the solar system contained bodies that did not orbit Earth, the phases of Venus, the first observational evidence not properly explained by the Ptolemaic theory, the rotation of the sun around a fixed axis as indicated by the apparent annual variation in the motion of sunspots. Galileo's work was truly revolutionary. With a telescope, Giovanni Zuppi saw the phases of Mercury in 1639. In 1687, Isaac Newton proposed universal gravity and the inverse square law of gravitational attraction to explain Kepler's elliptical planetary orbits. And we're going to talk much more about Newton towards the end, but of course his work is truly groundbreaking. The invention of the refracting telescope, and there you see an engraving of an early telescope from 1647. The telescope ranks with the invention of the compass as one of the most significant in human history. The earliest existing record of a refracting telescope was a 1608 patent submitted to the Dutch government by Middelburg spectacle maker Hans Lippershey. The actual inventor is unknown, but word of it spread throughout Europe. And think about the fact that the telescope now enables man to look at things he formerly could not see. With the telescope, man is now able to see things that only God has seen thus far in history. Man is literally getting a much wider view than what he had before. Various inventors continued developing the telescope and produced many different kinds. And of course, telescopes are with us today, and today they are very sophisticated, and they go into the far reaches of many parts of space to take pictures and send those back to NASA and other scientific bodies. Now, our discussion of the scientific revolution would not be adequate if we did not talk about Francis Bacon. The philosophical underpinnings of the scientific revolution were laid out by Englishman Francis Bacon, who has been called the father of empiricism. His works established and popularized inductive methodologies for scientific inquiry, often called the Baconian method or simply the scientific method. Bacon argued for careful observation of events in nature as opposed to philosophical arguments and deduction. So since from the time of the ancient Greeks, most scientific work was done by simply reasoning things out based on simple observations of common phenomena. But Bacon was advocating for what would come to be known and is familiar to us today with the idea of scientific experiments. Bacon was a devout Anglican. He believed that while the natural world can be studied inductively, knowledge of God can only come from special or divine revelation. Bacon also held that knowledge was cumulative and should be advanced, rather than just preserved. Knowledge is the rich storehouse for the glory of the Creator and the relief of man's estate, he wrote. And another quote from Bacon is, "A little philosophy inclineth man's mind to atheism, but depth in philosophy bringeth men's minds about to religion." A 19th century biographer of Bacon wrote, "Bacon's influence in the modern world is so great that every man who rides in a train, sends a telegram, follows a steam plow, sits in an easy chair, crosses the Channel or the Atlantic, eats a good dinner, enjoys a beautiful garden, or undergoes a painless surgical operation owes him something." And that quote is from Dixon's The Story of Lord Bacon's Life. Now, another early empiricist was William Gilbert, again, British, living from 1544 to 1603. Gilbert rejected both the prevailing Aristotelian philosophy and the scholastic method of university teaching. His book, De Magneti, or On Magnetism, was written in 1600, and he is regarded by some as the father of electricity and magnetism. In De Magneti, Gilbert describes many of his experiments with his model Earth, called the Terrella. From these experiments, he concluded that the Earth was itself magnetic, and that this was the reason compasses point north. Previously, some believed that it was the pole star, or Polaris, or a large magnetic island on the North Pole that attracted the compass. He was the first to argue, correctly, that the center of the Earth was iron, and he considered an important and related property of magnets was that they can be cut, each forming a new magnet with north and south poles. The English word electricity was first used in 1646 by Sir Thomas Browne, derived from Gilbert's 1600 New Latin electricus, meaning like amber. The term had been in use since the 13th century, but Gilbert was the first to use it to mean like amber in its attractive properties. He recognized that friction with these objects removed a so-called effluvium, which would cause the attraction effect in returning to the object, though he did not realize that this substance, electric charge, was universal to all materials. So as this early scientist is exploring magnetism, he's also, of necessity, coming to explore electricity because the two are related. Gilbert also studied static electricity using amber, a fossilized tree resin considered to be a gemstone. Amber is called electron in Greek, so Gilbert decided to call its effect, or the static electricity that is caused by rubbing a piece of amber, the electric force. He invented the first electrical measuring instrument, the electroscope, in the form of a pivoted needle he called the versorium. De Magneti was influential not only because of the inherent interest of its subject matter, but also for the rigorous way in which Gilbert described his experiments and his rejection of ancient theories of magnetism. Now, we come to the great thinker Galileo, the great thinker and scientist who has been called the father of modern observational astronomy, the father of modern physics, the father of science, and the father of modern science. Galileo lived from 1564 to 1642. His original contributions to the science of motion were made through an innovative combination of experiment and mathematics. Galileo was one of the first modern thinkers to clearly state that the laws of nature, or physical laws, physics, are mathematical. And if you study, if you take a college course in physics, you will soon run into the fact that there's a lot of math involved. You have Galileo to thank for that. Well, really God, but okay. In a work called The Assayer, he wrote, "Philosophy is written in this grand book, the universe. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures. His mathematical analyses are a further development of a tradition employed by late scholastic natural philosophers, which Galileo learned when he studied philosophy. His work marked another step towards the eventual separation of science from both philosophy and religion, a major development in human thought." So in other words, we're not just going to do thought experiments and reason our way to conclusions about the natural world. We are going to begin to conduct experiments. We are to test hypotheses, the basic scientific method, and we are going to begin to learn how to measure physical phenomena and so forth. Galileo was often willing to change his views in accordance with observation. In order to perform his experiments, Galileo had to set up standards of length and time so that measurements made on different days and in different laboratories could be compared in a reproducible fashion. And this is an important idea in science to this day. If an experiment cannot be reproduced, then scientists begin to question the results from experiments that cannot be reproduced. His ideas provided a reliable foundation on which to confirm mathematical laws using inductive reasoning, not deductive. Galileo's championing of Copernican heliocentrism was met with opposition from within the Catholic Church and from some astronomers. And if you recall in an earlier talk, when we spoke of the Roman Catholic Inquisition, Galileo was eventually hauled before the Inquisition. The matter was investigated by the Inquisition in 1615, which concluded that heliocentrism was foolish, absurd, and heretical since it contradicted Holy Scripture. Galileo later defended his views in The Dialogue Concerning the Two Chief World Systems, published in 1632, which appeared to attack Pope Urban VIII and thus alienated both the Pope and the Jesuits, who had both supported Galileo up until this point. He was tried by the Inquisition, found vehemently suspect of heresy, although not formally charged with heresy, and he was forced to recant or go back on his beliefs. He spent the rest of his life under house arrest. During this time, he wrote Two New Sciences, 1638, primarily concerning kinematics, the geometry of motion, and the strength of materials, summarizing work he had done around 40 years earlier. Galileo, a devout Roman Catholic, had considered becoming a priest as a youth, but his father wanted him to become a physician. He became interested in physics while studying medicine and wanted to become a mathematician. However, after accidentally attending a lecture on geometry, he talked his reluctant father into letting him study mathematics and natural philosophy, or science, instead of medicine. Galileo was also interested in the visual arts, and in 1588 obtained the position of instructor in the Accademia delle Arti del Disegno in Florence, teaching perspective and chiaroscuro. Chiaroscuro is the artistic application of various methods to produce the effect of light and darkness or shadows in art. Who does he remind you of? Does he remind you of anyone? Who was another noted Italian scientist, artist, inventor? Da Vinci, exactly, yeah. In 1589, he was appointed to the chair of mathematics in Pisa. In 1592, he moved to the University of Padua, where he taught geometry, mechanics, and astronomy until 1610. During this period, Galileo made significant discoveries in both pure fundamental science and practical applied science. He also had to continue staying away from the geocentric versus heliocentric universe controversy in order to continue working and teaching. So in other words, while he certainly advocated for a heliocentric system, you can get by with just not talking about it for a while and focusing on other subjects. Warned by Rome and the Jesuits not to continue holding to a heliocentric system, Galileo found it increasingly difficult to avoid upholding this heliocentric system. And if you're going to do significant work in astronomy, you can't go forward until you've determined which system you're going to adhere to. So by 1633, the Inquisition had found him suspect of heresy, forced to recant. They banned all of his works, including those that he would write in the future. They knew he wouldn't quit. His works had to be smuggled out of Italy to be published. And they were published in places like the Netherlands and England, places where there was more relative freedom. And what does this remind you of? If you remember back to when we talked about people like Tyndale and Coverdale, what had to be done with the works they were producing? They had to be smuggled out and published not in their home countries. His final work, Two New Sciences, was praised many years later by no less than Albert Einstein, and it was Einstein who called Galileo the father of modern physics, indeed, the father of modern science. Among his inventions or innovations are the use of the refracting telescope to demonstrate many astronomical principles and observations, geometric and military compasses, the thermometer, and the compound microscope. So innovations in grinding lenses and mirrors allowed human beings to look at the heavens through the telescope and also look at things that, very small things that previously man had never seen on the opposite end of the spectrum, things that can only be seen with a microscope, microbes and other very small things that we cannot see with the unaided eye. So once again, here's Galileo, a scientist, enlarging man's vision. Man is beginning to see many things that heretofore only God had seen. And of course, now we come to that great scientist. And again, if you study physics at all, you will, mostly what is taught in high school and college, at the undergraduate level, college physics is essentially Newtonian systems. So Sir Isaac Newton, PRS, President of the Royal Society, born December 25th, 1642, died March 20th, 1726 if you go by one calendar, 1727 if you go by another. There's interesting stuff going on, and this, you can take this as a homework assignment, I guess, if you want. There's interesting things going on with the measurement of time during this period, and you can research for yourself the Julian calendar and the Gregorian calendar. And you can study that on your own, and you'll find some interesting things. The measurement of time is very important if you're going to study the natural world. So Newton was an English mathematician, physicist, astronomer, theologian, and author. In his time, he was described as a natural philosopher. He is widely recognized as one of the greatest mathematicians and most influential scientists of all time, and as a key figure in the scientific revolution. His book, Mathematical Principles of Natural Philosophy, first published in 1687, established classical mechanics, physics. Newton also made seminal contributions to optics, the study of the refraction of light and what happens with light in the universe, and shares credit with German mathematician Gottfried Wilhelm Leibniz for developing the infinitesimal calculus. He developed, these two developed, or really uncovered, because obviously this was fully known to God prior to their discovery of the calculus, advanced mathematics by leaps and bounds. In the principles, Newton formulated the laws of motion and universal gravitation that formed the dominant scientific viewpoint until it was superseded nearly 3 centuries later by Einstein's theories of special and general relativity. Newton used his mathematical description of gravity to derive Kepler's laws of planetary motion, account for tides, the trajectories of comets, the precession of the equinoxes and other phenomena, eradicating doubt about the solar system's heliocentricity. Newton built the first practical reflecting telescope, different than a refracting telescope, and developed a sophisticated theory of color based on the observation that a prism separates white light into the colors of the visible spectrum. His work on light was collected in his highly influential book, Optics, published in 1704. He also formulated an empirical law of cooling, made the first theoretical calculation of the speed of sound, and introduced the notion of a Newtonian fluid. Now there's a term for further discussion and work. You could Google that. What is Newtonian fluid? I don't have time to tell you now what that is. In addition to his work on calculus as a mathematician, Newton contributed to the study of power series, generalized the binomial theorem to non-integer exponents, developed a method for approximating the roots of a function, and classified most of the cubic plane curves. And it's been so many years since I studied mathematics. I knew a little bit of those things long time ago. If you're a fan of mathematics, a lot of these things will probably be familiar to you. Among his contemporaries, his work in mathematics was said to have distinctly advanced every branch then studied. Newton studied at Trinity College, Cambridge, and became a fellow there in 1667. Fellows were required to become ordained priests in the Church of England, but Newton did not want to take holy orders. Although born into an Anglican family, by his 30s, Newton held a Christian faith that, had it been made public, would not have been considered orthodox by mainstream Christianity, with one historian labeling him a heretic. He studied early church writings extensively. Newton wrote extensively on religious topics, but kept all of his writings and views secret. And he was very successful within his lifetime at keeping all of this under wraps. Had he not, he would have been persecuted, just like Galileo, and perhaps worse, might have been put to death. But after his death, his religious works revealed that his view of the Arian controversy of the early 300s AD came down firmly on the side of Arius. The Arian concept of Christ is based on the belief that the Son of God did not always exist, but was begotten within time by God the Father. Therefore, Jesus was not co-eternal with God the Father. And in Newton's eyes, worshiping Christ as God was idolatry. Very, very not orthodox. Newton also owned and read several Socinian works, leading some scholars to conclude that Newton was a Socinian sympathizer. Socinianism is a collection of heretical beliefs that include rejection of the existence of Christ before the incarnation, and held that Jesus did not exist until he was conceived as a human being. Socinians also reject the idea of original sin and the substitutionary atonement of Christ to redeem man. Many scholars believe that Newton was essentially an anti-Trinitarian monotheist. Although the laws of motion and universal gravitation became Newton's best-known discoveries, he warned against using them to view the universe as a mere machine, as if akin to a great clock. He said, "So then gravity may put the planets into motion, but without the divine power, it could never put them into such a circulating motion as they have about the sun." Perhaps unwittingly, Newton serves as a preface to further developments in modern thought, leading to rationalism, deism, and the Enlightenment. So that concludes what I have and really all we've done here is we have scratched the scratches on the surface of the scientific revolution. And if you notice, if you've been following this, you will realize mostly I've been, with the exception of Galileo and Copernicus, I've been talking about a lot of English men. There were a lot of developments in the scientific revolution in Europe. I haven't mentioned any Germans. There were a lot of them. There were a lot of French scientists who were beginning to make all kinds of amazing discoveries in the 17th century. So time permitting, circumstances permitting, I may do an additional segment looking at the developments. For example, we've talked nothing about developments in chemistry and biology, but there were very important developments going on in those fields as well. Any questions or comments?